I wanted to do one of the problems that I didn't get to earlier today and show you how to solve something like that. We have here a charge of -3 nanocoulombs is located at the origin of a coordinate system, and a charge of 8 nanocoulombs is on the x-axis at x equals 2 meters. And at what two locations on the x-axis is the electric potential equal to 0? So I'm just going to draw a number line here to illustrate what's going on here. And pick a spot that can be the origin. And this is x in meters. And here's the origin, and here is 2 meters. And there's a charge here that is 8 nanocoulombs. And then a charge here that is -3 nanocoulombs. Now, remember the electric potential of a charge that's just a point charge there, V is equal to K sub E Q over R. And so it's inversely proportional to the distance from it is a way of saying that. Now, for a negative charge, the potential is always going to be negative. R is a distance. Okay, this is never negative. K sub E is never negative, but if Q is negative, the potential from that negative charge will always be negative everywhere. There's also going to be a potential due to this positive 8 nanocoulomb charge. It will always be positive because its Q is always going to be positive. Now, if this one's always negative, by the way, potential blows up when you get very close to the object because R gets smaller and smaller and you're dividing by a smaller and smaller value. So if we had a vertical axis here where we could plot the potential, for the negative charge, it would blow up in the negative direction. For the positive charge, it'll blow up in the positive direction here at 2. But in between those two, there must be a spot where it actually crosses through the origin. The negative potential from this one combined with the positive potential from that one must go from positive values to negative values somewhere here. And then out here, well, to the right, when you get far to the right from this thing, the 8 nanocoulomb charge is going to overcome whatever the -3 nanocoulomb charge does. In fact, it does it everywhere from here on over. And so you'd expect it to never go negative out here. But to the left of this is a smaller charge than that one. And when you get far enough away, it's going to be as if there's just a +5 nanocoulomb charge there. And so you'd expect the thing will go positive here, but it blew up negative as you got close to here. So somewhere to the left of that charge, you would expect that it'll be equal to the total potential will be equal to 0. So let's see another way of looking at that. And I made a spreadsheet where there it is, or maybe we'll just look at it here. Okay, hopefully you're looking at the spreadsheet now. I calculated the potentials, and for instance, for the positive, well, I'll do it for the negative one first. That's in column C here. For calculating the potential, I just ignored the K sub E. That's a proportionality constant that shows up in both. And so it's just a scaling factor in this case. So I had -3 divided by the square root of A2 squared. Well, A2 is the position X in meters. And the reason that I can just square it is because that negative charge is at the origin, and the X value is always the distance away from the origin, or it is if you square it and then take the square root. Squaring it makes a negative value positive, and taking the square root just gives us the positive value for an Excel function. So that's how I did the negative values. Now I had to do something when we got to x equals 0 because I get a divide by 0 error in Excel if I had tried to calculate the potential here. So I just made up a big value, negative value, and I don't graph that point anyway. It would actually be undefined at the x equals 0 point. The positive value isn't undefined at that point, and I was actually able to calculate it. Let me show you how. Oh, by the way, and again, coming down column A, everywhere, that's the position, X position in meters. For the positive value, since it's at the point X equals 2, what I did was I take 2 minus whatever's in A2 and square that and take the square root, and that'll give me the distance from -4 to 2 is what it ends up giving me. So that's the way I calculated that. And for the positive value, because it's got a charge of 8 nanocoulombs, I have 8 divided by the square root. And then over here, I've got an expression that actually calculates both of them. But I could just add these two things together to get that. And I didn't bother to, I actually figured out the both first and then thought it would be neat to see the individual ones. So let's look at the potential due to the positive charge. Got it graphed here. On this graph, the horizontal axis, here's the origin, crosses here. And you can see as the potential gets close to 2, it blows up in the positive direction, and then it diminishes as you get farther away from that, where the charge happens to be. And I carried it farther out on the left side than I did on the right because we're going to have a negative charge here at 0, and we want to see it kind of well as well. So here's the potential of the negative charge. Use red for it. And you can see it blows up in the negative direction when you get close to 0. And it diminishes in magnitude as you get far away from that point, but it stays negative all the time. The potential of the negative charge never goes positive. It gets close to 0, but never goes positive. And then for both of them, and I added a couple of things in here. One thing, I showed the potential due to the negative charge and the potential due to the positive charge. And then this dashed blue line here with long dashes is the sum of those two potentials. And you can see it does go to 0 somewhere between 0 and 1. But it's dropping down because the potential of the negative charge is kind of taking over as you get close to it. Then on the other side, as you start moving away from that negative charge, the negative charge value is getting lesser and lesser in absolute value. When you add to it the potential of the positive charge, it gets bigger and it actually crosses through, goes positive at something about -1. It's hard to tell from the graph, but and then goes positive. By the way, this dashed purple line across the middle here is the approximately where the potential is equal to 0, but I didn't place it quite right. It's a little bit too low. Anyway, let's see how we could do that mathematically and figure that out. Need to get my sharing back to here. Okay, back to this thing. Now, the total potential is going to equal the K sub E, Q for the positive one, times R to the positive one. This will be the distance to the positive one, plus k sub b for the q minus divided by the distance to the negative charge. Okay, now I have to set this up kind of carefully. It turns out it's not such a simple thing, and I don't want to have to be squaring things and then taking the square root of them. So I'm going to have an expression that should work for both. And let's pick a point in between 0 and 2, and it could be any of the points between 0 and 2, and we'll just call that point x. So how far is it from x to the negative charge? Well, it's just going to be x. And by the way, I'm interested in when this is equal to 0. So I'm going to set that equal to 0, and the first thing I'll do is divide both sides by k sub e. So I'll have q plus over r positive plus q minus over r negative equaling 0. And now I'm going to write those in. First, I'll have the 8 nanocoulombs over the distance to it, which I haven't figured out yet. So we'll see how that goes. And then I'll have the minus 3 nanocoulombs over the distance from this point over there. Well, it's just going to be x, and so I can write it as x. But how do I get the distance from this point to that? Well, it's just going to be 2 minus x. 2 is greater than x, so 2 minus x will always be positive. And so I can call it that, 2 minus x. And this is equal to 0. Well, another thing I can do is just cross out the nanocoulombs because I don't need those. And as long as I know that this 2 is meters, in fact, I could write meters on that. And now the only units I have in here are on the bottom of the fraction. Well, let's kick this across, and I'll have 8 over 2 meters minus x minus or is equal to 3 over x. I can cross multiply, and I'll get 8x is equal to, let's see, 3 times 2m is 6 meters minus 3x. Bring this across, and I'll have 11x is equal to 6 meters, or x is equal to 6/11 of a meter. Is that about what we would have guessed looking at the graph? Let's change our view here and go look at it and see what it turns out to be. Yeah, that's about what I'd guess. It's about halfway between 0 and 1. What was it supposed to be? 6/11? So a little bit more than halfway from 0 to 1. And you could have guessed that it was about 0.5 meters or something like that. We're not that far off. Let's see how we can do figuring out that other one. Come back to this thing again. Now I want to set up an expression where I'll have the Q positive, and let's see, I'll have an X value that's over here. So I can say this is where my X is going to be. Well, how far is it from 2 meters over to there? It's actually going to be 2 meters minus x. If x is negative, I'll actually end up adding something to it when I subtract x. So it's still 2 meters minus x is the distance to something that's over there. So it turns out this expression works for anything to the left of 2 meters. If I was to the right of 2 meters, I'd have to have x minus 2 meters to get that distance, but I don't have to. Anyway, what about for the distance to the origin here? Well, remember, x is going to have negative values, and I need to have a positive distance. How about 0 minus x, or just negative x? So I'll have q minus over negative x, which actually becomes plus q minus over x. Whoops. Yeah, and then we're going to have a negative value, and that'll equal 0 there. Let's see what happens when we take care of this thing. This will be 8 nanocoulombs there again over 2 meters minus x. Now, q minus is -3. Oh, I made a mistake. That should have been plus, and then this was negative. Because I copied the wrong expression. Until I put the charge up there, it didn't become negative. So I'd have plus, and I'll have a minus x and -3 nanocoulombs there, and that'll equal 0. So yeah, I think that should work out. Minus on top, minus on the bottom, and that gives me a plus. So let's see what happens. 8 nanocoulombs over 2 meters minus x is equal to -3 nanocoulombs over x. And remember, x is negative over here, or it'll turn out negative. We'll see what happens when we finally calculate this. Again, I can cross out the nanocoulombs. I've got them on every term or each side. And just multiply, cross multiply, and I'll get 8x is equal to -3. When I multiply -3 times 2m, well, I'll just do this first. Minus x, which is -6 meters plus 3x. Subtract 3x from each side, and I'll get 5x is equal to -6 meters, or x is -6/5 of a meter. So let's go look at our graph and see if that worked at all. Let's see, -6/5 is just a little bit more than 1 meter. And it's hard to tell here because I've got that dashed purple line on there that I probably shouldn't have stuck there. In fact, I'll delete it. So here you can see that the dashed blue line is actually crossing the horizontal axis a bit to the left of the -1 position. So it's between -1 and -2 and just a little bit past there. And that's probably about 6/5 to be -1.2. So that's just about what it predicted from the graph. And if I'd put more data points in my graph or used solid lines, we could have seen that even better. Oops, didn't come back to the right one. All right, so that's kind of an interesting problem to look at that and try to figure out places where the electric potential happens to be 0. It's very interesting to make a two-dimensional model of that. It used to be, there was a feature in Microsoft Excel that would let you make a kind of two-dimensional, actually it was a three-dimensional plot is what it was, and it would let you figure out the electric potential or visualize it, a two-dimensional potential field, see it in 3 dimensions. But and then you could in the old versions of Excel, you could grab it and twist it around and look at it from different directions, but they dumped that feature with new versions of Excel, unfortunately. However, interesting problem to do that. I think I'm still going to save these two problems for tomorrow. They're related to each other, and I just wanted to add this one short problem solution on there. So we'll see the solutions to those tomorrow.